In all the flow inlet and exit boundary conditions, what we will usually encounter is the direction specification. The question is, how does the flow enter? Let's say I specify a boundary to be a mass flow inlet. Then the question is, does the flow enter normally into the domain? So that's one possibility. You can say that the flow is entering indeed normally into the domain. So all the faces at the boundary, even if they are along a surface which is curved, which is not exactly planar in the same plane, even in that case, the flow will enter normally into the domain from these faces at the boundary. That's one of the possibilities. But we may also have situations when the flow is entering in at some angle or at some direction. So we can specify the directions either as a Cartesian in the Cartesian coordinate system, or the global cylindrical coordinate system, or local cylindrical coordinate system. The local cylindrical coordinate system, in addition to specifying the radial, tangential and axial components, we also need to define what is the position of what is the location of the local coordinate system with respect to the global one. So in this way you can even generate a local coordinate system at the inlets and specify the tangential, radial and axial components of the flow coming into the domain. Now that we are familiar with how we can give the inputs in terms of a constant value or a parameter, or let's say a user-defined function or profile, and that we are also familiar with how to specify the direction of the flow, let's look at how to give the different inputs within the specific boundary types. So let's say we start with velocity inlet. So basically it was intended for incompressible flows, but it is also possible to use it in version 13 and further releases for compressible flow calculations. It is inspired by the practice which is made anyway in ANSYS CFX. Usually you need to specify the velocity magnitude and the direction, and if it's a 2D axisymmetric case, in that case also the swirl velocity can be specified. In addition to the velocity magnitude and the direction, we also need to specify something called the supersonic or initial gauge pressure. I'll be speaking about this static pressure value in the next slide. Just hold on. And in addition to this, dependent upon the turbulence model or any other model that you have included, also those specific inputs can also be included for temperature, or let's say if I'm specifying turbulence, then in that case turbulence can be specified in terms of, let's say, intensity and hydraulic diameter. Just to give you an idea about the turbulence parameters, turbulent intensity and hydraulic diameter is what usually people follow in the industry. You can also specify, let's say I'm using a K epsilon turbulence model, I can also specify the value of K and epsilon at the inlets, but that's not usually known from experiments. Usually what we can say is if the flow is highly turbulent or low turbulence. A turbulent intensity of 1% means a very low turbulent. This is usually encountered in very gentle breeze of wind. And if I have a turbulence something like 2 or 3% or even 5%, these are somehow moderately a bit on the higher side of turbulence. But if it is something like 10% turbulent intensity, it's a very highly turbulent flow. So depending upon your application, you can specify the turbulent intensity. The hydraulic diameter is defined as 4 times the cross-sectional area divided by the perimeter of the boundary that you're speaking about. So 4a cross-section upon perimeter. That's how you can find out this. For a circular face, it comes out to be the diameter of the given circular surface. So let's say we have a cylinder flow through a cylinder. In that case, the inlet diameter itself is the hydraulic diameter. So in this way you can specify the turbulence specifications. There are some other means by which the intensity and other specifications can be given for turbulence parameters, but this can be explored more by just visiting this help option available on the velocity inlet or any other inlet boundary dialog box. But let's say we have some other models also included. Let's say radiation modeling is being done, or chemical species or combustion multiphase kind of models have also been included. Let's say we are having multiple species simulation. In that case, we also need to include what are the different compositions of the different species which are entering with this velocity of 0.25 of the single phase. So these specifications depend very much on the models that have been included in your problem. Let's just have an idea about what this supersonic or initial gauge pressure means. There are two conditions under which this value is important for us. One situation is when, let's say, the flow becomes supersonic just downstream of the velocity inlet. So if it becomes supersonic, then the velocity inlet value is not respected anymore, but whatever value that you specify here is treated as the static pressure. This is the static pressure which will be used. If you are a bit familiar with compressible flow studies of a CD nozzle or even a converging nozzle, you will know that once the flow becomes supersonic, it does not take the upstream velocity value or total pressure value. Whatever you specify as the static pressure, that is more important for it, because of the theory behind the compressible flows through such under such supersonic conditions. And in that case, it is this value that you specify is used as the gauge static pressure. Mind you, Fluent operates only with gauge pressure values. We'll speak about this in the next few slides when I speak about the pressure inlet boundaries. So gauge pressure is what it is used. It is always with respect to the operating pressure which you specify in the operating conditions panel. And the other situation when this value can become important is when you want to initialize the flow through standard initialization process in ANSYS Fluent. So if you initialize it from this boundary, then in that case, this is the static pressure which will be used to assign in every part of the domain. Because what you do in standard initialization is you just specify the value everywhere in the domain to be a specific value. So if you want to initialize it from the let's say this velocity inlet, then everywhere in the domain the velocity will be assigned to be 0.25 meter per second according to the direction of the inlet through which the flow is coming in, and this static pressure which you specify will be given as the static pressure everywhere in the domain. So only in these two cases it will be used. Otherwise, if the flow is incompressible and you don't plan to initialize with this inlet pressure, then in that case this value is actually not going to be used at all. Now let's come down to the pressure inlet boundary. As I mentioned to you, Fluent basically deals with pressures only in the gauge terms. So actually the gauge pressure in association with the operating pressure together constitutes what is called the absolute pressure, and it is the absolute pressure which we use to calculate, let's say, density variation according to an ideal gas law or a real gas law. So it is the absolute pressure which actually defines the total energy per unit volume of a gas or a fluid. But basically, just removing the operating part from it, what we get is the gauge pressure value. This is what usually we would be able to calculate using a pressure gauge. If you're using a pressure gauge to calculate the pressure inside the room that we are in, then what we'll be getting is with respect to the atmospheric conditions, which is the operating pressure in that case. So where we set up this operating pressure is to go on the operating conditions panel through define operating conditions, or it's also available on the model tree, besides the model tree in the descriptions panel. So basically the gauge pressure has its significance in this, that it is helpful in reducing some round of error. I'm going to speak about this in the coming slides. What we usually require for pressure inlet boundary, therefore, is the total pressure. Mind you, it's the total pressure, but in gauge terms. So we don't include the operating pressure. We speak with respect to the reference pressure, with respect to the operating pressure. We specify the total pressure value at the inlet. And again, the supersonic initial gauge pressure has the same sense. If I initialize the problem or if the flow becomes locally supersonic, then this static pressure value is used. It doesn't use anymore the gauge total pressure value. It can be used in buoyancy driven flows. If I don't know the flow rate or the velocity, then in that case it can be used as a free boundary, especially in external or unconfined flows, and it assumes a loss free transition from the pressure that you have specified to the inlet conditions. So it does not contain any loss coefficient. If you want to include some loss coefficient, you should define it to be an inlet vent. In that case, you can also include the loss coefficient. So Fluent calculates the static pressure and the velocity at the inlet during the course of the simulation, and the mass fluxes through the boundaries dependent upon the velocity are also calculated accordingly. So the basic inputs which are required for pressure inlet are the total gauge pressure. So it defines the total energy which will drive the flow. We need to specify the direction in which the flow is entering in, and it should not include the hydrostatic pressure. If you are having gravity effects also, you should not include the hydrostatic pressure part. So this will be automatically calculated by Fluent. And the if there are some additional models included like energy equation or turbulence parameters, they also need to be additionally given as inputs. For incompressible fluids, this total pressure that you specify, using that, the Fluent can calculate the static pressure once the velocity is clear from the domain. So dependent upon the flow solution inside, the static pressure and the velocity values can be calculated according to the Bernoulli's equation. For compressible flow calculations, it uses the isentropic compression law. So the total pressure that you specify will be used to calculate the static pressure and the Mach number. Using the Mach number, the velocity can be calculated, which is Mach number is equal to the velocity upon the speed of sound under those conditions. So in this way, the overall dynamic part can also be taken into account. For compressible flow calculations, while doing these calculations, we just add the operating pressure to it. If you can recollect this, the reason is because this equation should have the absolute pressure, so absolute total pressure and absolute static pressure together. This ratio is coming out to be this term, and using this, the velocity components can be found out for compressible flow calculations. And the density in such cases is associated with the static pressure. So it's a static absolute static pressure which is used to calculate the density according to this ideal gas law, where R is the gas specific gas constant. It's not the universal one. So it also includes the universal gas constant and the molecular mass of the gas that you have in your problem. And once this is done, then using the static temperature and the total temperature can be found out if we know the velocity field. The other type of boundary which is quite popular, especially for compressible flow calculations, is the mass flow inlet boundary. The mass flow inlet boundary has its significance, especially for situations when we know the mass flow rate, or at least we know the mass flux. So it's a better choice. It's if we have the possibility, the better choice would be to use pressure inlet, because usually to maintain a constant mass flow rate is not so easy for us. Usually we use devices like a pump or a compressor, which can have control over the pressure rather than the mass flow rate. But it is also something which is available, of course, for our problem. If we can always maintain a constant mass flow rate, then this is something which we can also give as an input for our given CFD simulation as a boundary condition. And it is not so necessary. If it is an incompressible flow, we can very well give a velocity inlet boundary in that case. The inputs that are required usually are, we can specify the inputs in three ways, either as a mass flow rate or a mass flux, or a special kind of boundary condition for mass flow rate boundary condition is the mass flux with average mass flux. This is primarily meant for mixing plane model in dealing with multiple reference frames. So this is something which I'll discuss in a separate lecture when we are dealing with some advanced topics of moving deforming zones kind of problems. But here most of the time we'll be done with mass flow rate, which specifies kg per second or kg per minute or kg per hour of mass coming inside, or mass flux would be per unit area the mass flow rate. So this can also be specified. The other inputs like supersonic or inlet static pressure and flow direction specifications remain the same as described for other boundaries so far. And we can also include, if there are additional inputs, additional models, then in that case some inputs are required for the total temperature. Mind you, for pressure inlet and for mass flow inlet, the specification required at the inlet is the total temperature or the stagnation temperature. It's not the static temperature, unlike for velocity inlet. And other inputs for dependent upon the models can also be included. Now let's move on to the outlet kind of boundaries. So let's look at the pressure outlet boundary. So this is something which is basically specifying the static pressure at the outlet. There is something new coming up in ANSYS release 13, that we have the flexibility to specify an average pressure specification of the static pressure. So at the outlet boundary, it's not zero pressure everywhere on the face on the outlet, but it's averaged over the whole surface. You can have the average pressure specification of whatever value which you specify. So usual practice is to specify this to be zero, which means it is the pressure at the outlet is the same as the operating pressure, which is typically the case that we try to operate under atmospheric conditions or whatever operating conditions, and usually the outlet is exposed to it, exposed to the outside environment. If the flow becomes supersonic, though, if in case of a compressible flow, then the value at the outlet, the pressure at the outlet will be extrapolated from the flow in the interior. But in the other cases, basically this is the pressure value which is used. There are also backflow conditions. In case the flow comes back into the domain, then because of a lower pressure upstream of the external phase at the outlet, there can be flow which is being sucked inside. So this can also happen. This can be primarily because of some geometrical features, or because of in the beginning of the simulations, when you specify a wrong initialization, there can be some backflow which will subside after some time as the simulation process goes. There can be situations when backflows are really expected, but in either case we should give appropriate backflow conditions so that we can remove any kind of convergence difficulties and we can really get realistic values. One of the suggestions which is made as a best practice in among the CFD community is to extend the domain at the outlet in case there is a backflow occurring. But most of the time we can avoid it if we give a good initialization. If we expect that there should be backflow, then appropriate conditions have to be given. It's suitable for compressible as well as incompressible flows. As I mentioned to you, release 13 has an additional input for average pressure specification. So the zero pressure, that whatever you specify is averaged over the whole surface at the outlet. Another kind of boundary, especially for free stream conditions under compressible flow calculations for very far away from, let's say, the airfoil. If you are doing an external aerodynamic analysis, in that case is use the pressure far field boundary condition. So we specify the free stream Mach number and the static pressure conditions. It's only applicable when you're using the ideal gas law for calculating the density of the fluid inside, or we can specify the static pressure and that which is in gauge terms again, and we can also specify the Mach number, and the direction specification can also be made along with the turbulence specification. So the inputs required are the static gauge pressure, and the Mach number can be subsonic or supersonic, and the flow direction as we have described already. And there is nothing like a normal to boundary in this case. It's only a specification of the direction which you give in the user panel in the dialog box. And if there are additional models, the inputs accordingly change. In this case, we have to specify the static temperature. The other kind of outlet boundary condition is the outflow boundary. In outflow boundary, it is primarily meant for incompressible flows. So when the flow goes out and we are not so much concerned about what is the pressure, we don't know the pressure. In that case, for incompressible flows, we can use a velocity inlet or a mass flow inlet, and we can specify an outflow boundary, but we have to be aware of what are the limitations of using the outflow boundary. As you can see here, in this case, using an outflow boundary at a place where the flow is not yet fully developed would be quite wrong. So it's not possible to use the outflow boundary if the flow is still developing. The flow should be fully developed, only then the outflow boundary can be given. Second, there are some limitations. Secondly, for outflow boundary, for example, the pressure inlet boundary condition cannot be used, because then the solver doesn't know what is the pressure inside the domain, so you don't have a unique solution of the pressure. Therefore, this is an ill-poised or a underspecified problem. It cannot be used with compressible flows, as has already been mentioned, and it's primarily meant for incompressible flows. And also, if the density is varying, it's an incompressible ideal gas equation is being used for density variation. You cannot use it in the case of an unsteady flow. But otherwise, outflow boundary is quite helpful, especially for flow through series of arteries, let's say, or piping structures. We can specify the flow rate weighting. Let's say there are multiple outlets which have been specified as outflow boundaries. We can give a flow rate weighting of 0.5 each, and equal amount of mass will go out of each of these outlets. So in this way we can control very much the outflow boundary conditions as well. No other inputs are required in the case of outflow.